Hello, people. This is Justin Livingston, and today we're going to be going over the relationship between electric fields and electric potential. And so, basically, first we're going to start out by defining the terms, and then we'll try to put together a relationship between the two through equations. And then we're going to do a problem example just to kind of help you comprehend what we're going over today a little bit better. And so, first, we're going to start off by going, what exactly are electric fields? And so, electric fields are shown by electric field lines and they surround charged objects. And so, we can see over here to the right, we have a positively charged object and a negatively charged object. And these electric field lines act differently between the two, and they act as vector quantities, which mean that they both have a direction and a magnitude. And so for the positively charged object, these lines are going to face outwards. They're going to go away from it. But as for the negative, it's going to be opposite. The field lines are going to go towards the negatively charged object. And with these lines, when they're in a non-uniform field, meaning that there's just one charge, these lines will extend all the way to space forever. They're not going to stop. They're continuous. And whatever else is in this field created by these charged particles, they're going to experience the charged particles are going to exert a force, or the charged objects are going to exert a force upon those objects as well. And so we just kind of describe what would happen if it's in these objects are in a non-uniform field, but they're in a uniform field. Let's say that this positively charged object, this negatively charged object are like right next to each other. And these electric field lines are going to extend forever, and I'll demonstrate with this pen what would happen. So when these two are placed together, then the electric field line from the positive will go towards the negative, positive to negative, and then also positive to negative. And these lines aren't continuous. They have a beginning and end. It's always going to start from a positive charge and it's going to end in the negative charge. And this is what we call a uniform field, where basically the lines have a beginning and an end. And that's the next thing we're going to go over is that not only are these created by charged objects, but electric fields can be created by a difference between potential energies or difference in voltage. And so next, let's go over what exactly electric potential is. And electric potential is described as the amount of work needed to move a charge from a specific point in an electric field to another point within the same field. And instead of being viewed as a vector quantity, electric potential is actually viewed as a scalar quantity, which means it just has it doesn't really have a direction, but it does have magnitude. So there's a numerical value you could put towards it. And that numerical value is actually potential energy per unit charge. And so what exactly does that mean? So electric potential is actually related to gravitational potential, where basically kinetic energy and potential energy are correlate with work. But in an electric sense, we kind of remove the kinetic energy from the equation, and we basically directly correlate potential energy to work. And potential energy, or the delta, the change in potential energy, negative delta potential energy equals work. And the potential energy or electric potential is actually directly correlated to the potential difference or the voltage. And so what exactly does that mean? So in this next slide, we're going to kind of see the relationship between what exactly the relationship is between electric field and electric potential. And it's best shown in a uniform field, like we were talking about, where there's a charge plate over here, a positively charged to negative. And it's easiest to tell here just because you're able to apply the equations just to kind of visually see it. So Let's first go over these equations. So up here we have change in volts or potential difference. And I didn't explain it super well earlier, but basically voltage equals potential difference, or the difference in potential energies. And so, as stated before, electric potential within electric field is the amount of work needed to move this positively charged particle from the positively charged plate to the negatively charged plate. And the amount of work needed is directly correlated to the potential difference that, as stated above. And also electric field um, also relies, or the electric field strength relies on the potential difference and the distance. And so basically, to help you comprehend, or just to kind of sum it up, we're going to go over an example, just kind of so you can see how electric field strength and electric potential relate. And so we're going to use a uniform environment where we have two charge plates, as in the previous slide. And the question is, there are two parallel conducting plates that are separated by 12 centimeters, and one of them is taken to be at 0 volts. And so we're always going to give the positively charged plate the lower voltage. And so in this case, it'll be 0 volts. And what is the electric field of the potential? 6.7 centimeters away from the 0 volt plate is 350 volts. What is the voltage between the two plates for part B? And so let's first tackle part A. What is the electric field strength of the potential? 6.7 centimeters away from 0 volt is 350 volts. And so you're probably thinking like, oh man, we don't have all the numbers in order to solve this equation or this question, but we actually do. So we're going to use from 2 slides ago the equation: the electric field strength equals the change in voltage over the distance. And so the good thing is with electric field strength, it actually doesn't change within this field, so it's the same throughout. And so the distance equals 6.7 centimeters, and the voltage equals 350 volts. And so we're just going to plug and chug. And so it'll be 350 volts, but we're going to convert the centimeters to meters. And we need to do this for every equation that we use distance in. And so the answer should be 5,223 newtons per coulomb, which is interesting because, as I said before, electric field exerts a force within on any object within this field. And so newtons is actually the same unit that we used for force. So that's how it's correlated with the amount of force needed. And so part B is, what is the voltage between the two plates? We're going to use the equation, but we're going to just rearrange the equation from last time. And as I said before, the electric field strength doesn't change. The distance does, so the distance changes the volts. And so I'm gonna plug and chug again, and the answer we should get is 626 volts. And so you can see here, sorry for the bad writing, but the potential difference is what created this electric field. And also we know that within this electric field, this charge is moving from the positive to the negative plate, being caused by electric potential, and the potential difference is what causes the field strength. And so basically, it's kind of hard to narrow down the exact relationship between electric potential and electric field. But basically, I believe the two main things that you need to know is electric potential is the amount of work needed to move a positive charge from one point to another inside an electric field, and that both electric potential and electric field are reliant on potential difference or voltage. And so I hope this video helped you better comprehend the relationship between the two. And here are the materials I used. I just used regular PowerPoint and OpenStack's college physics book um, to relay this information to you. And I hope you enjoyed it, and I hope you have a great day.